What department?
Physics?
Physics.
Hi everyone, good to see so many of you here today. As Wendy said, my name is Valentina. I transferred from Santa Barbara City College to UCSD as a physics major. This summer I've been fortunate to work with my mentor Rustin Mirsaflavi and my faculty advisor Carl Reinhardt on some very interesting research. Our project title is the detection of substances of forensic significance using microfluidics and surface-enhanced Raman spectroscopy. From now on, I'm just going to say SERS. So the main big picture of our research is that we're trying to develop a method of detecting substances of low concentrations in fluids using these microfluidics devices that we built in our lab. And while this may sound abstract, it actually has numerous real-world applications, such as testing someone's blood for trace amounts of drugs or even explosives. And this is useful in homeland security. It's also applicable in medicine. Many drugs like heroin and fentanyl show the same symptoms, so when someone comes in for an overdose, they generally get treated for both, which causes a lot of harm on their body. So with this device, you could just run a quick blood or saliva test and see what they've taken and treat accordingly. It's also applicable in drug trafficking in the sense that you can test the purity of your drug for harm reduction purposes. So again, fentanyl is a cutting agent for heroin, but it's many more times stronger than heroin. The problem is that drug dealers can mix the two together, and people take the same dosage as if it was just heroin. So overdoses are common, and many people die. So just like you can go places for clean needles, the idea is that you could also test your drug for things like fentanyl and see what dosage could potentially kill you. So the devices, because of the material that we use, they're fairly inexpensive and also reproducible. So there's some potential for manufacturing at a macro scale here. The reason we use microfluidics in SERS, for microfluidics, it gives you precise and predictable control over small amounts of fluids. So by adjusting things like the length of the microchannel, you can control things like the speed of the fluid and in turn control what processes you want to occur. SERS is a powerful tool that lets you identify molecules based on their vibrational nodes. So all molecules, based on their structure, can vibrate in different ways. If you shoot a laser at it, they can absorb some of its energy into vibration. By looking at how much energy was absorbed, you can figure out what that molecule was. And that's regular Raman spectroscopy. Surface-enhanced Raman spectroscopy basically utilizes metal to enhance the normal Raman signal by a factor of 10 to the power of 10 times. And we use silver nanoparticles to achieve this. So, some goals for... I don't want to update you. Some goals for the summer. Our main goal that we're still working towards is to be able to relate the Raman spectra to the concentration of a substance. We want to do this because when we look at complex media such as blood or street heroin, which typically has a lot of things in it, we want to be able to not only detect the presence of a substance, but also its concentration. And this you can do by looking at the area under the peaks of its spectra. These are related to the concentration. And we want to find this relationship in order to apply it in the future. Before we can do that, we kind of have to go the other way around and work with known concentrations. So we mix our own solutions and we test them and get their spectra. And from that, we can start building up this relationship. Lastly, as a personal goal, was to learn to build these microfluidic devices. And luckily, over the course of 8 weeks, I've had plenty of practice. So these three goals do a good job in outlining the three main methods that are present in our research, namely device manufacturing, data collection, and data processing. So I'm going to talk more about the data collection aspect of our research since that's currently the most important part of it. So split that up into 3 parts. First one being sample preparation. So we mix our own solutions in order to work with established concentrations. So we work with about 0.1 to 100 micromolar of the analyte or sample. We also use flow salt or lithium chloride and silver nanoparticles, which are 20 nanometers in size, and I'll explain why we use those later. And then we load our microfluidic device in this fashion. So salt and silver go kind of in the back inputs here, and the analyte goes in the middle input. And then we apply a vacuum in order to initiate the flow. And this laser is just showing the region which we will be looking at later, which is shortly after that intersection of the three input fluids. So next step is to secure the device in the microscope, and after you apply the vacuum, the microfluidic processes kind of kick in. And if you look at that same region, which I mentioned earlier, it will look something like this. So you might see how the flows are kind of separated here. This is actually called a laminar flow, and this is caused because the microchannel create a lot of friction against the fluid, so it slows it down enough basically so that when they meet there is no turbulence and they don't mix. The only mixing that occurs is through diffusion. So some of the silver nanoparticles will come down here, and the salt will come up here, and the salt will induce aggregation of the silver nanoparticles in this middle region where the sample is for the analyte. So basically, the aggregation of the silver nanoparticles around the analyte will create hotspots for the SERS signal, and this is the reason why we look in this region. Lastly, so you've mixed your solutions, you've loaded your device, and you put it in the microscope and applied the vacuum. Now all that's left is to basically shoot a laser at it. So we use a 633 nanometer laser to map a section of the microchannel shortly after the intersection of the inputs. Each device is run about 4 to 5 times, and after each time we just turn on the microscope, take a look, and see if there are any air bubbles or basically anything blocking or preventing the flow, and then we just keep running it. And we usually stop after 10 to 12 minutes because then it just gets too aggregated and the signal has to get messed up. I included some pictures here. After 5 minutes, you can see that the aggregation is starting to kick in. After 10 minutes, it looks almost like a pitch black line. This is generally when we would stop. So I'm going to show you some of the best data that we've got. This is Noscapine and Papaverine, and also PDMS, which is what the device is made out of. So this is going to be present in all data. And there's also a background signal, which most likely originates from citrate, which is present in the silver nanoparticle solution. So this is also present in all data. On the y-axis, we have normalized intensity measured in counts. On the x-axis, we have Raman shift, which basically says how much energy from the laser was absorbed by the substance. We also have some reference spectra for heroin and 6-monoacetylmorphine. These were not run through the device, but rather obtained by drop and dry. So we just take the analyte, we mix it together with the silver nanoparticles, bake it in an oven, and then shoot the laser at it. And this is how we get this. And same here, intensity, normalized in counts, and Raman shift. So just a wrap up of what we've done during those 8 weeks. In terms of lab work, I've learned to build microfluidic devices and also run the Raman microscope, which is how we get our experimental data. Also got to go in the clean room to see Rustin make a silicon wafer, which is what we use for a mold to make our microfluidics devices. So that was really cool. For Papaverine and Noscapine, we got 100 micromolar data, which I just showed you, and also reference spectra. We have heroin, morphine, which I didn't show you, and 6-monoacetylmorphine. Lastly, future work. We would like to test a broader range of concentrations, especially for Papaverine and Noscapine, and also to obtain data for the substances that we currently only have references for. And when we have all this experimental data, we can start building up this spectra concentration relationship that I mentioned earlier. So I'd like to thank the AIM Photonics program and ICB for sponsoring this research, my mentor Rustin and faculty advisor Carl Meinhardt for teaching me all this and supporting me in furthering my research. The Moskowitz and Meinhardt lab groups for all their interesting talks and lab meetings. And lastly, my program coordinators, Wendy and Jens, for putting all this together. It's been a very good experience. Thank you.